Gaseous State Part 2, presented by G. Satyanarayana, Assistant Professor, Department of Chemistry, Dr. B.R.R. Government College, etc. In this discussion, we learn about the units of Waals constant, Wonderball's equation under different conditions. This is how can we modify the Wonderball's equation under different conditions of temperature and pressure, critical phenomenon of gases, and isotherms of CO2. Now we discuss about units of A and B. In last class, we have discussed about the derivation of Wonderball's equation. Based on the postulates of kinetic molecular theory of gases, we have made corrections to pressure term and volume term, so that we have derived Wonderball's equation of state in case of real gases. In that equation, we can see the constants A and B. We can see the constants A and B. Here we have given the equation of Wonderball's equation, which is applicable to the real gases. Is it? So P plus AN square divided by V square into V minus NB is equal to nRT, where V should be the capital. Okay, this will be the capital. So P plus AN square by V square into V minus NB is equal to nRT. You know that P and V are the pressure and volume of the gas. N is number of moles. A and B are called as Waals constants. Now we are providing the values, providing the units of Waals constants. Let me discuss about the units of A. In this equation, P plus AN square by V square, this term, represent the pressure term. This P plus AN square by V square represent the pressure term, whereas V minus NB represent the volume term. So PV is equal to nRT. That is ideal gas equation, but that equation cannot be applied to the real gases under all conditions. In order to apply in case of real gases, you have derived the Wonderball's equation. In this P plus AN square by V square represent pressure term, and V minus NB represent volume term. So P plus AN square by V square represent the pressure term. That's why this AN square by V square also represent the pressure term. That's why AN square by V square is equal to units of pressure. That will be equal to units of pressure. Is it? So AN square by V square is equal to units of pressure. What will be A? Means from this you are writing equation for small a. So A is equal to pressure units into, this becomes V square by N square. What are the units of pressure? We can write atmospheres into V square means liter square divided by N square means mole power minus 2. These are the units of small a. So what are the units of A? It is atmosphere, liter square, mole power minus 2, or we say bar. Is it bar? And meter power 6. Meter cube represent the value is meter power 6 and mole power minus 2. That also we can write it. That are the units of A. Or we can also express like this: atmosphere decimeter power 6 mole power minus 2, because 1 liter is equal to decimeter cube. Like that also we can express the units of A. Okay. So P plus AN square by V square represent the pressure term. In that AN square by V square again represent the pressure unit. Okay. Based on that you are writing equation for A, then you are providing the units. Like that we have produced the units of A. Let us see about the B, units of B. B is called as covolume or excluded volume. In this equation, B minus NB represent the volume term. So NB also will have the units of volume. That's why NB will have the units of volume. What is B? If you write equation for B, is it from that you can write equation for B, you have to shift this N in this side. Means you can shift the small n towards RHS. When you shift small n towards RHS, it becomes n power minus 1. That's why the volume units are liters. When you shift this n in this side, what do you get? N power minus 1. That's why we get mole power minus 1. So liter mole power minus 1 is a unit of B. That is a unit of B. So A units are atmosphere liter square mole power minus 2, whereas B units are liter mole power minus 1. They are the units of A and B. That is the Wonderball constants. Let me see the values of A and B. Is it values of A and B? These are expressed in, the A value is expressed in atmosphere liter square mole power minus 2, whereas B is expressed in liter mole power minus 1. Hydrogen 0.246, A value, B value 0.0266, helium 0.034, B value is 0.0237, neon 0.21 A value, B value is 0.0171, oxygen A value is 1.36, B value is 0.0318, nitrogen A value is 1.39 and B is given as 0.0319. For methane it is 2.25, 0.0428, and hydrogen 3.67, B value is 0.0408, sulfur dioxide 6.71, 0.0564. That the different values of A and B. The values of A and B depends on nature of gas. Means different gases will have different A and B values. Different gases will have different A and B values. That you have to remember. Next, what is importance of A? That is a very important concept. So A is the measure of van der Waals forces, the attraction forces. A is the measure of intermolecular attraction forces. Greater the intermolecular attraction forces, greater will be the value of A. That you remember. Greater the intermolecular attraction forces, greater will be the value of A. So that the gases which are having, but the gas molecule which are possessing highest or greater A value are easily liquefied. Why the gases with greater A value are easily liquefied? Because the intermolecular attraction forces will be more. The intermolecular attraction forces, that the van der Waals forces existing between the molecules of gas will be more. That's why these type of gases are liquefied easily. Now we can see this table which is having the highest A value. Sulfur dioxide is having the highest A value. That's why we say sulfur dioxide is easily liquefied. Intermolecular attraction forces are more in case of sulfur dioxide in this table if you see. And also hydrogen chloride the next position, then methane, then after that you can see it is nitrogen. Like that we can predict the magnitude of van der Waals forces existing between the molecules of a gas. So A is useful to predict the amount of or magnitude of intermolecular attraction forces. Have you observed in the case of helium it is 0.034. It is having the smallest A value. That's why it cannot be liquefied very easy. Similarly in case of hydrogen also. Hydrogen or neon, you can see that. They are not easily liquefied. Hydrogen and helium and neon. Because the intermolecular attraction forces are very less in these cases. Like that, A is a measure of magnitude of intermolecular attraction forces existing in the gases. That is the importance of A. Next, we discuss about the van der Waals equation under different conditions. Under different conditions means What will be the form of van der Waals equation under high pressure? What will be the form of van der Waals equation under moderate pressure and very low pressure? That we see how we can modify these van der Waals equation under different conditions. Here we have given the van der Waals equation. Again, for n moles we have given here P plus An square by V square into V minus Nb is equal to nRT. P is pressure and V is the volume of that gas. Now we are observing the van der Waals equation under high pressure. This is a condition imposed. What is the condition? The gas is present under high pressure. The gas is present under high pressure. So when the pressure term is more, means this P is more because the gas is present under high pressure. Compared to this, the term of An square by V square can be neglected because this P is very large. When you compare that An square by V square, correction factor, what we say, is it that will be very, very small. That will be very small. That's why this An square by V square can be neglected compared to what? Compared to this pressure. This An square by V square can be neglected compared to P. Why? Because under high pressure, P value will be more. In comparison, An square by V square can be neglected. So that now this equation becomes, you see, P into this one, P into V minus Nb is equal to nRT. This is for n moles of gas we are writing. P into V minus Nb is equal to nRT. Okay, you expanded PV is equal to nRT. Again, you are shifting this side, is it? PNB. For 1 mole gas, N becomes equal to 1, is it? N becomes equal to 1 for 1 mole of gas. That's why we can write how PV is equal to RT plus PB. PV is equal to RT plus PB. This is the, what we say, van der Waals equation under high pressure. We can apply this to the gas which is present under high pressure. Let us see about the compressibility factor. Compressibility factor Z is equal to PV by RT. Okay, Z is equal to PV by RT, that we say is the compressibility factor of that gas. But what is the relation between PV and RT? You remember from this what we write? PV will be greater than RT. PV is greater than RT by what quantity? It is PB quantity. PV is greater than RT by PB quantity. So, PV is greater than RT. So, what is the compressibility factor you see? Z is equal to PV by RT. Z is equal to PV by RT. In this, PV is greater than RT means numerator is more than the denominator. When the numerator is more than the denominator, Z will be greater than 1. So, under high pressure, Z will be greater than 1. Under high pressure, what will be the value of Z for real gas? It will be greater than 1. That means the gas shows positive deviation. When the gas shows positive deviation, what is the inference? We say the gas molecules are suffering from repulsive forces. Why they are having the repulsive forces? Because the gas is present under high pressure, so that the gas volume will be contracted, the intermolecular distance will decreases, so repulsive forces will be dominate between the molecules of the gas. Like that, we can also see the value of Z. Z will be greater than 1 under high pressure. So what is the form of van der Waals equation under high pressure? That is very, very important. You remember it is PV is equal to RT plus PB. This is very important. PV is equal to RT plus PB for 1 mole of gas. Okay. Next, let me see about the van der Waals equation of state under low pressure. Very low pressure we are writing. At very low pressure we are writing. At very low pressure, what happened? Volume will be very large according to Boyle's law, because P and V are inversely proportional. volume is very large. When the volume is very large, you see, P plus AN square by V square, where the volume is there in the denominator. Denominator is very, very large. Means what will be the value of fraction? What is that fraction? AN square by V square. You see the value of AN square by V square fraction. Here V is very, very large. And the denominator is very, very large. This AN square V by V square will be very small. AN square by V square will be very small. That's the first point. Means compared to P, AN square by V square can be neglected. Compared to P, in the first term, pressure term, AN square by V square is neglected. Why we are neglecting that? Because at low pressure, V will be very large. When the denominator is very large, the fraction will be very, very small. The value of fraction will be very, very small. That is the reason. You see the second factor, volume term. Under very low pressure, volume is very large, we said. Means compared to capital V, NB will be very, very less. Compared to capital V, NB will be very, very less. That's why here NB can be neglected. Mean two terms you are neglecting here. What is the first term you are neglecting? It is AN square by V square is the first term. What is the second term? NB, that you are neglecting. After neglecting these terms which are having the smallest values compared to the remaining present in those values, what we get? PV is equal to nRT. What is PV is equal to nRT? It is nothing but the ideal gas equation. Means at very low pressure, the gas behaves ideal. Under very low pressure condition, is it? The gas behaves ideal. This already we have discussed the gas state part 1. Under which conditions the gas behaves ideal? At very low pressure and high temperature, the gases will behaves ideal. Means under high temperature condition also we can see same situation. Under very low pressure or high temperature. Under these two conditions we can see the same situation. Means the gases behaves ideally. Here you are neglecting two terms, that is AN square by V square as well as NB. Okay, this is second case. At moderate pressure, you see, at moderate pressure, only NB can be neglected compared to V. At moderate pressure, volume will be also moderate. Here you cannot neglect this AN square by V square. Just you can neglect this NB only. Compared to V, NB will be small. Compared to V, NB will be small. That's why this can be neglected. When this is neglected, you see the remaining factor P plus AN square by V square into V is equal to nRT. Or you shift this AN square by V, after multiplying you see P into V, PV, that is equal to nRT. AN square by V square into V means how much you see? And V get cancelled. What is the remaining factor you see? AN square by V. Means you are shifting this AN square by V square into V towards RHS. Clear or not? So PV is equal to nRT minus AN square by V. For 1 mole of gas, N will be equal to 1. That's why how can we write this equation? PV is equal to RT minus AV, A by V. PV is equal to RT minus A by V for 1 mole of gas. Compare the value of PV and RT, which is greater. If A by V is subtracted from RT, then only it becomes equal to PV. Means RT is greater than PV. Or we say PV is less than RT. PV is less than RT by what quantity? A by V quantity. PV is less than RT by what quantity? A by V quantity. Now you can see the compressibility factor. What is the compressibility factor? Z is equal to PV by RT. But we have seen that PV is less than RT. When numerator is less and denominator is more, what will be the fraction value? It will be less than 1. Z will be less than 1. Means the gas will show the negative deviation. We have discussed the values of Z in first lesson, is it? Z is equal to 1 for ideal gas, Z is greater than 1 or Z is less than 1 for real gas. If Z is greater than 1, it shows positive deviation, and also it indicates intermolecular repulsive forces. If Z is less than 1, it is called a negative deviation, and it indicates intermolecular attraction forces of that gas system. So here, Z is less than 1 means the gas will show the negative deviation. At moderate pressure, the gas will show the negative deviation because Z is becoming less than 1. It shows the negative deviation and the molecules will have the attraction forces, intermolecular attraction forces. Okay, now next, if you see the hydrogen and helium gases, these molecules are very, very small. In case of hydrogen and helium, these molecules are very, very small. So they will show the exceptional behavior. You can see the exceptional behavior by hydrogen and helium. What is the reason? Because these molecules are very small and will have the low molecular weight. So the intermolecular attraction forces are very, very less. Intermolecular attraction forces are very, very less. Let us see the Wonderball's equation for 1 mole. This Wonderball's equation for 1 mole where we have substituted n is equal to 1. Since these molecules are very small and having meager van der Waal forces, means weak van der Waal forces, that's why A value will be very less. Already we have seen in the table, A value is very less, so that A by V square can be neglected. Because if A is very less, numerator is very less, A by V square becomes very, very small. Compared to P, this A by V square can be neglected. This A by V square can be neglected. Why we are neglecting? Because the value of A is very, very small. You see, the value of A is very, very small. If value of A is very small, A by V square will be very small further. Compared to P, this can be neglected. When you neglect here, the term here, you see PV minus PB. Is it PV minus PB is equal to RT, or PV is equal to RT plus PB? And Z is equal to PV by RT. We know that PV is greater than RT again. We have got this under high pressure region in previously, just now we have discussed. So PV is greater than RT, then what happens? Z will be greater than 1. Means the hydrogen and helium always show positive deviation. What is the reason? Because they are having the small size and the value of AV is very, very small. That is the reason. Okay, like this we can explain the exceptional behavior of hydrogen and helium. Okay, so under high pressure, Z becomes greater than 1. At very extreme low pressure, Z is equal to 1. Under moderate pressure, Z is less than 1. This we have discussed. Based on that, we can write the van der Waals equation. We can modify the van der Waals equation. Okay, next you see this graph. This discussion can be seen in this graph. The graph is drawn between Z versus P, is it? That means the compressibility factor versus P, where Z is equal to 1.0. So that is ideal gas equation that represents the ideal gas. In case of hydrogen and helium, how it will be? It will be always a positive deviation. Under high pressure or under, what we say, moderate pressure, it will be always a positive deviation. Only positive deviation. What is the reason? The reason is A will be very, very small because intermolecular attraction forces are very less. Next, under extremely low pressure, all gases will behave as ideal. Extreme low pressure, PV becomes equal to nRT. Next, at moderate pressure, you see in the moderate pressure what happens? Not in the case of hydrogen and helium, remaining gases. In case of remaining gases, at moderate pressure, as the pressure increases, negative deviation increases. Is it that is less than 1 here? But under high pressure, again it will becomes Z greater than 1. This can be seen. Means behavior of gases can be explained. Real gases can be explained. Behavior of real gases can be explained with help of Wonderball's equation. That is the concept here is. Right. Next topic is critical phenomenon of gases. What is meaning of critical phenomenon? Suppose a closed vessel is there. In that closed vessel, a liquid is placed. Then what happens? The liquid will now evaporate to fill the space which is present above it. Is it? A closed vessel is there. Now the closed vessel is partially filled with a liquid. And total air is, let's say, evacuated. Under that condition, what happens? The liquid will vaporize. And the vapors of the liquid will be filled in the space which is present above the liquid surface. Then what happens? The liquid vapor equilibrium will exist. In that situation, after some time, we can see liquid vapor equilibrium. Liquid vapor equilibrium will exist between the liquid and when we see the liquid vapor equilibrium, when the rate of evaporation becomes equal to rate of condensation. Under that condition, we can see the formation of equilibrium between liquid and vapor. Under that condition, it is possible to us to see the clear boundary. You can observe a clear boundary. Means separation, a clear separation between the liquid as well as vapor surfaces in the closed vessel. Means at room temperature, suppose if we observe the water under given experimental conditions, the saturated water vapor and the liquid will exist in equilibrium. There we can see a clear distinction or clear boundary between the water vapor as well as liquid water at room temperature. But as the temperature increases, what happens? Rate of evaporation increases. Rate of evaporation will increases and the vapor pressure also increase. Vapor pressure also increase. Like that, we can see the liquid vapor equilibrium in case of water between 25 to 100 degrees centigrade very clearly. Between 25 to 100 degrees centigrade, we can see the liquid vapor equilibrium in case of water, that is in closed vessel. But when the temperature reaches to 374.4 degrees centigrade, high temperature, that is 374.4 degrees centigrade, then what happened? The meniscus fades and disappears. Means a boundary separation which we are observing between the liquid and vapor now will disappear. The meniscus which is present between the liquid and vapor, then that will disappear. At this temperature, liquid and vapor of that water exhibit the same physical property. What are the physical property? For example, the density or vapor pressure. Means at 374.4 degrees centigrade, the liquid and vapor are cannot be distinguished separately. Under this temperature, it is not possible to distinguish the liquid as well as vapor. Is it? So this state is called critical state of water. Critical state of water. This type of states can be observed in case of all gases or all liquids. So every gas will have its own critical temperature, characteristic critical temperature that depends on nature of the gas. Means under critical conditions, what happen? Critical point or the state, critical state, it is not possible to distinguish the vapor and liquid of a substance. This point or state is called critical state. Let me see about in order to explain the concept, let me see the Andrews isotherms of carbon dioxide. What are Andrews isotherms of carbon dioxide? What is meaning of isotherm? Isotherm is a graph which is drawn at constant temperature. In case of carbon dioxide, we are observing the pressure volume relationship at different temperatures. Is it? The study provides different graphs at different temperatures. All these curves are called isotherms. So the graph is drawn between the pressure versus volume of carbon dioxide. Okay, let me see the behavior of carbon dioxide at 13.1 degrees centigrade. What happens? Now you observe the point A here. Observe the point A. When the gas is present at point A, it is having certain volume. This is a volume. You can see it on the volume axis. Now what happens? We are increasing the pressure at constant temperature. What is the temperature we have selected? 13.1 degrees centigrade. So at 13.1 degrees centigrade, carbon dioxide is present at state A, let's say. Now you are increasing the pressure. What happened when you increase the pressure? Gradually, volume decreases. Like this, it is decreasing. You see, the volume is decreasing from A to B like this. This is the gas state. That's why you can observe here the shape of the curve as a rectangular hyperbola, somewhat rectangular hyperbola. Because A and B represent the gaseous state of carbon dioxide, so represent the rectangular hyperbola. Next, after reaching this point B, now what happened? Means you are increasing the pressure gradually. When you are increasing the pressure, the volume decreases, intermolecular attraction forces will increases. Intermolecular distance is decreasing, so that what happened? Intermolecular attraction forces will increase, so that after reaching point B, then liquefaction will start. Liquefaction of CO2 will start. When the liquefaction of CO2 is started, spontaneously the vapor of CO2 will convert into liquid. No need to use any pressure. The CO2 gas molecule itself convert into the liquid. Means from B to C, we can see the liquefaction part. B to C, it shows the liquefaction part. Like this. So, total gas is liquefied at point C. After reaching the point C, is it? Again, if you use any pressure on that, because in liquid state, the molecules will be very close to each other. Suppose if you are using any pressure on that liquid, you can see a small change in the volume, steep. Means you are using the high pressure like this. High pressure is observed. So that volume change will be very, very less. Decrease in the volume will be very, very less. So at 13.1 degrees centigrade, you are observing three parts here. One is A to B, gas state. B to C, gas and liquid states. Both of them are existing here. From C to D is only the liquid states. Like these three parts you are observing in the case of CO2 at 13.1 degrees centigrade. Similarly, in the case of under 21.5 degrees centigrade, let us see another temperature. Initially, carbon dioxide present at F state. When you are using the pressure, volume decreases up to, maybe it is E, or this is E state, let's say, E. So, when you are applying the pressure, volume decreases up to F. After reaching the F, liquefaction will start. So, liquefaction will start at F, and that will continue up to G. Here liquefaction will complete. So GF represent what? Liquid vapor equilibrium. Liquid gas equilibrium, or you say. After G, suppose if you increase the pressure further, so the steep line is obtained. Why a steep line is obtained? Because decrease in volume will be very less on increasing the high pressure. Decrease in volume will be very less, is it? And this line indicates that. Here also you can see three parts, where E to F is gas state, F to G is a liquid and gas state equilibrium, and G to H is the only liquid state. This is observed at 21.5 degrees centigrade. Means Under these two temperatures, 13.1 and 21.5 degrees centigrade, we can see a clear distinction between the liquid and vapor. Either it is in between B and C, or you say it is F and G. But when 30.98 degrees centigrade is maintained, now the gas is present here, and gradually we are applying the pressure. When the pressure is applied, volume decreases gradually. After reaching this point P, suddenly it will convert into liquid. Suddenly what happened? The gas state will convert into liquid state at this point. After that, you can see what? Only the liquid state. So at point P, it is not possible to, here it is. At point P, it is not possible to distinguish between the liquid and vapor, as we have seen between F and G as well as B and C. Here B and C and F and G. Between these, you can see the liquid vapor equilibrium. But here you cannot see the liquid vapor equilibrium. And between B and C and F and G, you can see the clear meniscus or distinction between the liquid and vapor. But at point P, at 30.98 degrees centigrade, it is not possible to see this distinction. Means it is not possible to see the meniscus between the liquid and vapor. The gas suddenly converts into liquid state. This point is called, P is called critical point of carbon dioxide. At what temperature we got it? It got at 30.98 degrees centigrade. Means we say 30.98 degrees centigrade is the critical temperature of CO2. Next you see the just 31.1 degrees centigrade. Just maybe 0.102 degrees centigrade more, is it? Here it is A, and you see what is present. What is the temperature? 31.1 degrees centigrade, just higher than this 30.98 degrees centigrade. Now if you apply the pressure on that gas, it gives a rectangular hyperbola. Means the gas will not undergo liquefaction even though you are using the high pressure. Similarly, we can see the same thing at 48 degrees centigrade. If you use the pressure, gradually if you increase the pressure, only we can see the gas state. The curves are up, having which shape? Rectangular hyperbola shape. Is it? So, it is not possible to liquefy CO2 above 30.98 degrees centigrade even though by using high pressures. Is it? It is very clear now. What is the point here? We have to concentrate. Above 30.98 degrees centigrade, it is not possible to liquefy carbon dioxide even though by using high pressure. But below 30.98 degrees centigrade or at 30.98 degrees centigrade, it is possible to liquefy CO2 by using pressure. Yes, it means 30.98 degrees centigrade is a temperature above which CO2 cannot be liquefied, below which CO2 can be liquefied, or at or below 30.98 degrees centigrade, CO2 can be liquefied. So this 30.98 degrees centigrade is called as critical temperature of CO2. Like this, every gas will have its characteristic critical temperature. Above critical temperature, it is not possible to liquefy that gas by using the pressure. But below critical temperature or at critical temperature, it is possible to liquefy the gas by using the pressure, by applying the pressure. Like that, how can we define the critical temperature? Critical temperature is a temperature above which the gas cannot be converted into liquid or cannot be liquefied by applying pressure. The temperature is called critical temperature. What is the critical temperature of carbon dioxide? It is 30.98 degrees centigrade. Below critical temperature, how many states you can observe? 3 states you can observe. One is the gas state, second is equilibrium between the liquid and vapor or gas, third is the liquid state. But at a critical point, it is not possible to distinguish liquid and vapor or liquid and gas. At critical temperature, the physical properties of liquid and gas will have same physical properties. At critical temperature, the liquid and vapor of gas will have the same physical properties like vapor pressure or temperature. Okay, so the critical temperature of CO2 is 30.98 degree centigrade. Every gas will have its own characteristic critical temperature. Now we can see the definitions of critical temperature. It is the minimum temperature above which the gas cannot be converted into liquid state even at high pressure. That is called critical temperature. It is indicated by Tc. What is critical pressure? Pc. How can we define? The pressure of the gas under critical conditions. When a gas is present at critical temperature, that pressure of that gas is called critical pressure. Similarly, we can define the critical volume. In order to define the volume, you have to fix the pressure and temperature. That's why we are defining in the following way. The volume of 1 mole of gas present under critical temperature and pressure is called critical volume Vc. So every gas will have this critical constant. Tc, Pc, Vc are called critical constants. So critical temperature, critical pressure and critical volumes are called critical constants. Whereas A and B are called they are called as Wonderball's constant. Okay, is it clear or not? Like that, we can understand the concept of critical phenomenon of gases with help of Andrews isotherms of CO2.